When you've completed this lesson, you should be able to identify ordered pairs in Cartesian coordinate system. You'll also be able to read and interpret line graphs in real-world scenarios. And you should be able to draw graphs when you're given a table of data. Photonics technicians need to know how to draw, read, and interpret graphs. And you'll work with graphs on a Cartesian coordinate system to do that. You may know this as an XY graph or a Y versus X graph. In real-world examples, however, don't usually come with Y's and X's, so you may encounter things like an oscilloscope voltage V versus a time T, or a graph of the laser cavity parameters G1 versus G2, or laser beam irradiance I versus the position X across the beam diameter. Here's an example scenario that you may encounter as a photonics technician. You have a graph of the beam power versus the ratio A over W, which is the measurement of the size of the aperture the beam is passing through, to the beam spot size, W, as shown here. And you may have to know how much laser power gets through a circular aperture when that radius A equals the beam spot width. In other words, A over W is equal to 1. Or, for a laser beam spot size W, what is the ratio of the radius A to the spot size W if only 50% of the power is getting through? Or, what is the minimum value of A? What's the smallest A can be in order for all of the laser beam power to get through that aperture? These are the kinds of questions that you may have to answer working with your lasers as a photonics technician, and we're going to learn how to do that in this module. For now, we'll put these questions aside and review some of the skills necessary to answer this question. Consider the two explanations below for using a three-prong plug adapter. Clearly, a picture is worth 1,000 words. You would much rather look at the photograph or the drawing to find out how to use a three-prong plug instead of reading word by word directions. So that's what a graph is good for. A graph will help you identify trends in the data, such as increasing or decreasing or reaching a maximum and then falling off. And that's where a picture can be worth 1,000 words compared to a table of data. The Cartesian coordinate system that you're going to be using in this module was developed over 350 years ago by a French soldier named Descartes. He started with a simple number line, and you've seen this since elementary school, so this is probably familiar to you. From negative numbers out to positive numbers with 0 in the middle. We'll call this our x-axis, and you know that how to locate values on a number line. For example, x equals 2, or x equals negative 3, or if x equals 0. 0 is also known as the origin or the 0 point. And that's a terminology that you'll need to become familiar with in this module. The x value specifies the horizontal position on our coordinate plane. Then we'll draw a second number line and orient it perpendicular to the first, crossing at the origin y. The vertical number line is labeled the y-axis. We can locate values on the y-axis too. Y equals 5 and y equals negative 2, for example. And we can identify points that have both x and y values. For example, x equals 4 and y equals 3. Together, we call the two values an ordered pair. That's a term that you're going to have to be familiar with and use frequently in this module. An ordered pair specifies both x and the y value, as we said in the previous slide. So we have x equals 4 and y equals 3, and that's going to help us plot the point xy equals 4, 3. So every point on the Cartesian coordinate system can be identified by an ordered pair of x and y values. Everywhere out here. Over here we can plot points. We can plot points over here, or over here. Any place out there can be plotted on the Cartesian coordinate system with an ordered pair. The x value, or the first number in the pair, specifies how far left or right you want your point to be. And the y value, or the second number in the pair, specifies how far up or down you want the point to be. Example 2 asks you to identify an ordered pair for a point A that's out there on the Cartesian coordinate system. So first find that x value by finding out how far A is over from the y-axis. How far over did you have to go? In this case we went 3, and so the first part of our ordered pair is 3. That will be the x value. Then the y value is how far up that point is, and you can see that we moved the point up 2 units, and so our ordered pair for this point is 3, 2. So we'll say that A is equal to 3, 2 on the order, as an ordered pair. Similarly, for point B, first find the horizontal distance, 2, then find the vertical distance, 3. And so the ordered pair for B is 2 and 3. Continuing example 2, you'll notice an important difference between the ordered pairs A and B. A is 3, 2, and B is 2, 3. Order makes a difference. That's why we call it an ordered pair. The first value is always the x coordinate, and the second value in the ordered pair is always the y coordinate. What ordered pair would you write for point C? The answer is negative 4, 1. You'd have to go x first is negative 1, 2, 3, and 4. And that was negative 4. And then the y value is just up 1 unit. So that would be positive 1. Here's some more points. Can you identify their ordered pair values? Well, here's the answers revealed. If you didn't have time to get them all, you can back up this video and try to look at it again. D is minus 3 over and minus 3 down, so it's minus 3, minus 3. E is over x with 4 and then down 2, so it's negative 2. F is another one up in the top corner there, and that's over 1 and up 4. So that would be 1, 4. Notice the signs of all the x and y values in our examples of ordered pairs. Both of them are positive here. Here we've got x's are negative and y's are positive. Here we have x's that are negative and y's that are negative. And here we have x's that are positive and y's that are negative. Our Cartesian coordinate system is actually divided into 4 quadrants because of those signs that you see on those numbers. They're traditionally numbered quadrant 1, Roman numeral 1, Roman numeral 2, quadrant 2, Roman numeral 3 for quadrant 3, and Roman numeral 4 for quadrant 4. Let's complete the statements now about the ordered pairs in each of the 4 quadrants. All points in quadrant 1 have x values that are what? Either positive or negative, and y values that are either positive or negative. What would you supply there? Oh, you're right. Positive and positive. X values are always positive and y values are always positive up there in this first quadrant. Very good. How about quadrant 2? If all these points were over here, what x values and y values would they have over there? You're right again. Negative x values and positive y values. Very good. All these x values over here are always negative, and the y values are always positive. Okay, you know where we're going. Quadrant 3. What about all the points in quadrant 3? Sure, you know it. They're both negative. All the x values are negative and the y values are negative. All right, this is the hardest one. Quadrant 4, what do we have? Sure, it's the only thing that's left. They're going to be positive and negative. So you'll notice that the x values are all positive and the y values are all negative. So that's the trait that you're going to notice for each of the 4 quadrants. Quadrant 1 is plus and plus. Quadrant 2 is negatives and positives. Quadrant 3 is both negatives. And quadrant 4 is positive and negative. Now you don't really have to memorize this, but it'll become very useful to you as you begin to make your own graphs to realize that there are certain quadrants of the Cartesian coordinate system that have positive and negative values. Now, when you're graphing with many points, each point is plotted on the graph as an ordered pair, an x and a y value, just like we've been seeing. The relationship between x and y can become evident by how the appearance of those dots. So here you've got what looks like a straight line of relationship. As x gets larger and larger, sure enough, y gets larger and larger, and you'd probably expect more dots to continue off for greater x's and greater y's. On this one, you'll notice that there's a downward trend and then there's an upward trend. And you can see that very clearly with the values. It may not be quite so obvious in a table of values, but you can see it clearly in the graph of those ordered pairs. Here's a graph that says what? It says the y values stay basically the same and don't ever change, no matter what x does. So that's telling you something too. And here you plot some data points and what do you think about that? Well, it's probably not very clear, is it? And that's also good information because you may have thought there was a relationship between x and y, and when you plot it you realize, well, there may not be a relationship between x and y. Maybe my cable got unplugged when I measured those things. So the graph is very helpful, and learning to read a graph is a very important skill as a photonics technician. Reading a graph is very important. And the first thing you should do when you read a graph is note the labels on the axis. What are we graphing here? We're comparing temperature in degrees Celsius with temperature in degrees Fahrenheit. And which ones are the x values? X values are the Celsius temperatures, and the y values are the Fahrenheit temperatures. So the ordered pairs out here would be first the x value like 40, and next the y value like maybe 100. Next thing you need to notice is what are the units of measure for each x's and y's. In this case we're graphing Celsius degrees, and y will be Fahrenheit degrees. And next we should note what are the scales used to mark each axis. How much does each division represent? Well, we look at the scale markings and we go 0 and skip 1 and then 20 and skip 1 and then 40 and so on. So each grid mark here represents what? 10 degrees of Celsius. So if we had numbers beside every one of these grid marks, it'd be 0, 10, 20, 30, 40, and so on. How about the vertical axis? A little different here, isn't it? We go 0, skip 1, and then 40, and then skip 1, and then 80. So each grid mark here would be 0, 20, 40, 60, 80, and so on. So there's a difference in the vertical scale and the horizontal scale when it comes to the magnitude of the numbers. Is the scale the same on each? No, we've already observed that it's not. And where's the origin on this graph? Is it shown? The origin is where 0 and 0 are, so the origin is actually right here and not over here. So we've actually shifted the origin because we're allowing for some negative values of Celsius. So here's an example of reading a graph. We'll look at that Fahrenheit temperature graph. What Fahrenheit temperature corresponds to 20 degrees Celsius? Well, you observe that graphed relationship between the F and C. That's that blue line. Let's find 20 degrees C on the horizontal axis. follow that line up till you hit the graph dot for 20 degrees C. That would be the X value for that dot. Now we want to find out what is the Y value for that dot. When we move over to the Y-axis and find out that it's about 70 degrees Fahrenheit. So for this graph, we would estimate the ordered pair of that dot is 20 degrees Celsius and 70 degrees Fahrenheit. How about the other direction? What Celsius temperature corresponds to 32 degrees Fahrenheit? Again, we would find 32 degrees Fahrenheit. This time it's going to be on the Y-axis. And we need to follow the horizontal line over to the dot that's plotted there, the point that's plotted, and determine what is the X value that corresponds to that. Follow a vertical path down until you find, in our case, about 0 degrees C. This is just as we expected, right? 32 degrees Fahrenheit corresponds to 0 degrees Celsius. And the ordered pair there would be what? Would it be 32, 0? No. I almost got you, didn't I? It's going to be 0, 32. 0 degrees Celsius, 32 degrees Fahrenheit, because you always put the ordered pair with X first and then Y. Now what if we wanted to read that graph for a temperature that didn't happen to have a dot there? Well, that's called interpolating. And what Fahrenheit temperature corresponds then to 50 degrees Celsius? So this is an example we can try interpolating. So we're going to find 50 degrees Celsius on the horizontal axis and move up just like we did before, this time until we hit the line. We won't encounter a dot this time. We're going to have a line that goes between two dots and hopefully truly represents the relationship between Fahrenheit and Celsius. We call this interpolating, and now we find over that the Fahrenheit temperature that corresponds to that is 120 degrees Fahrenheit. So again, the ordered pair for this relationship would be 50 degrees Celsius, 120 degrees Fahrenheit. And similarly, what Fahrenheit temperature corresponds to 110 degrees Celsius? How far does our line go? It only goes out to about 100. So sometimes you might need to have values beyond those shown on the graph, and that's called extrapolating. When you extend the graph, that can be a little risky, all right? So we have to do this with some caution. If we extend that line out there and follow the 110 degree C vertical all the way up until you reach the extrapolated graph line and then move over, and we have to estimate what the F would be on this case, it would be about 230 degrees F. It's almost off our scale. We might need to even extend the scale in addition to extending the line. And we'd estimate about 230. And so the ordered pair for this relationship would be 110 degrees Celsius, 230 degrees Fahrenheit. So we can also observe trends on this graph. Look at the titles and labels on this graph. We're comparing what? We're comparing pressure versus time. And this graph is not a straight line like the Fahrenheit Celsius graph we just looked at. They're looking at pipeline pressure of pressure versus time. It shows a trend that might not be evident from just a table of values, but it looks like things are going downhill, doesn't it? Looks like not only is the pressure dropping, but it appears to be dropping faster in the afternoon than it did in the morning. Probably not a good sign for this pipe. Spotting trends like that is a common use for time graphs. Read the values from this graph just like we did before. At 8 a.m. the pressure was 660 psi. At 11 a.m. we have to interpolate a little, but we'll do that with these points and find that the pressure was about 648 psi. And what was the pressure at 6 p.m.? We're going to have to extend that line. What's that called? Extrapolating. We're going to have to extrapolate that graph past 4 p.m. and predict the pressure at 6 p.m. That doesn't look like you're quite as confident about doing that. With this, who knows? It may have dropped a whole lot more, or it may have recovered and started dropping less. we just don't feel quite as confident about extrapolating this graph, and that's one of the dangers about extrapolating. So let's look at the general steps for drawing your own graph. First thing you should do is decide on a title for the graph. So let's pick, our data is going to be some rainfall data. So we're going to pick a title such as Rainfall in April. We look at our data and we've got weeks and number of inches of rain each week. So that'll probably identify our two axes in our graph. We determine which one should be X and which one should be Y. We're going to label week as the X-axis and rain as the Y-axis. We'll plot the ordered pairs one at a time, going over X values and up Y values. And we'll draw a straight line or perhaps a curve through the plotted points. Sometimes you just draw what we call a best fit line if we expect a linear relationship. We don't necessarily expect a linear relationship for rainfall, but we can see a trend in this rainfall data. It's simply dropping off as the weeks went by in April. As things warmed up, less and less rainfall came to this location. Here's another one. Given voltage and current measurements that are perhaps illustrating Ohm's Law, let's make a graph of these voltage and current ordered pairs. A good title for this graph would be Ohm's Law, since that's what we're showing. And the axes for this would be probably voltage from 0 to 50 and current from 0 to 5. We usually choose the independent variable as the horizontal axes, and so we're going to guess that the person who took this data probably turned up the voltage in 10-volt increments and then measured the current rather than the other way around. And so that would make voltage the independent variable, the one that was being controlled, and current the dependent variable, which would be the one that would go on the vertical axis. So let's draw and label the axes in our graph. Ohm's Law is our title. Voltages in volts are our x-axis, and current measurements in amperes form our y-axes. So now we'll plot each of those points on the graph, starting off with 0 and 0, 10 volts and 1 amp, 20 volts and 2 amps, 30 volts and 3 amps, 40 volts and 4 amps, and finally 50 volts and 5 amps. And we can probably pretty much line this up with a straight line to connect the dots, as this is a very dependable relationship in a very good circuit, well behaved. Now, where is Ohm's Law in this graph? You remember Ohm's Law is voltage is equal to the current times the resistance. Well, we've got the voltage and the current. Do we have the resistance on here? Well, we can rewrite that as I times R, or the current times resistance, equals the voltage V. And we can solve for I by dividing both sides by R, the resistance, and we get I is equal to 1 over R times V. And that happens to look a lot like a linear relationship that you may have recalled from your math classes of y is equal to mx plus b. In this case, b is 0, the intercept is 0, but we do have y is equal to something times x, some slope, that is, times x. And so the slope in our graph happens to be 1 over r, the inverse of the resistance. So, since the slope is the change in y divided by the change in x, we have in this case, if we look at our line, we have the change in y is 2 amps, and the change in x is 20 volts. That would be 2 amps divided by 20 volts is equal to 0.1 amps per volt. That's our slope for this line. And since the slope is equal to 1 over r, then r would be equal to 1 over the slope, and we can put our slope value down in the denominator. 1 divided by 0.1 will give us a value of 10, and the units will invert also, which would be volts per amp, which just happens to be equal to ohms. And so sure enough, our resistance for this circuit must be 10 ohms. And we found that out from measuring the slope of our graph. So now I think we're ready to tackle this opening scenario problem that you saw. We're going to find first how much laser power gets through that aperture when it's equal to the laser beam spot size. So when A is equal to W, then the ratio of A over W will be 1. Let's locate the ratio of A over W equals to 1 on the x-axis and move vertically up until you intersect the power transmission curve. From that point, you move left and read on the y-axis about 0.86 or 86%. So about 86% of that laser's power will get through that aperture when the aperture is the same size as the beam spot. Now the next part of this question asks, what is the ratio for a pass-through of 50% of the beam power? In other words, what will be the proportion of A to W when half of the power is blocked by that aperture? Well, to find that, we need to find the 50% mark on the y-axis, and we'll move across horizontally until we intersect the curve, and then move down to read the value on the x-axis of about 0.6. So 50% of the laser's incident power will pass through when the aperture is about 60% of the beam diameter. Isn't that interesting? Instead of being 50%, it's about 60%. And the last thing it asks us is, what is the minimum value of that aperture? What's the minimum size of that aperture for which essentially all of the laser beam power will get through? Inquiring minds would like to know. So let's find out. We'll locate 1 or 100% on the y-axis, and as before, we'll move across till we reach the curve. This time it's a little harder to ascertain where it really hits the curve, but we'll just sort of guess it's right there, and move down from that point, and we come up with about 1.6. So when the aperture is about 1.6 as large as the beam diameter, all of the laser's power can make it through that hole. That's a pretty interesting result, isn't it? Alright, so let's take a look at some of the practice exercises. This is your chance to build up your confidence and to see some real-world scenarios of problem solving with graphs and rectangular coordinates. First one is given a graph of total highway mileage as shown here. You're going to be practicing reading some graphs here. So what type of vehicle does this graph describe? Well, you look at the graph and you look at the legend, and you can see that it's passenger cars and trucks and buses. So there's two sets of data on this graph. The square little dots and the round little dots distinguish between the two types. So you have to look at that closely to know which one is which. And what span of time does this graph cover? Well, again, you look at the graph closely. You have two clues. You have it in the title, and you also have it in the x-axis, which is the years for this data. So it's from 1945 to 1995 data. Next, which type of vehicle is increasing its annual mileage at a faster rate? Faster means it's rising more rapidly, right? So it looks like the overall slope for the passenger cars is steeper than the trucks and the buses. So we would have to say that the passenger cars are increasing their mileage faster. Now it says estimate the trucks and buses mileage in 2000. Uh-oh. This is that issue of extrapolating, and this is a little iffy, as we know, predicting the future. But it looks like if things continue in the same trend as they have been, the result would be about 550 billion miles. Seems reasonable for the highway mileage traveled by trucks and buses in the year 2000. Exercise 2 is going to give you another chance to practice reading a graph. This one's got three relationships on it. We're comparing crop yields to average temperature rainfall, and what units are being used for the crop yields. Well, you can see from the y-axis, bushels per acre is being used, and the average temperature is along the horizontal axis, the x-axis, in degrees Fahrenheit. And looks like three different graphs. We have 1 inch of rainfall, 3.5 inches of rainfall, and 6 inches of rainfall. So now, how can you identify the data from these three different rainfalls? What's the secret? Well, just like in the previous graph, you have a legend or a key, and that key shows you that the 1 inch rainfall is a solid line with no little bullets or dots on it. The 3.5 inch rainfall is a dashed line with no dots, and the 6 inch rainfall is a solid line with dots. Now, isn't it much easier to see all that with the color I've added? So use your color skills when you're making your graphs, if at all possible. You don't have to keep them black and white anymore. Third part of exercise 2 says, alright, for an average temperature of 82 degrees, what crop yields can one expect with a rainfall of 6 inches, or for 1 inch? So let's first look at the 6 inches. You go up the curve, just like we've learned to do in this lesson, and then hit the data point, and then you'll go across to the left, to the y-axis, and you'll read about 75 bushels per acre when the rainfall is at 6 inches. Now, for a 1 inch rainfall, we'll find 82 degrees Fahrenheit on the horizontal axis when we go up, and over to 37 bushels per acre. Now, for an average temperature of 70 degrees, do higher yields come from heavy rainfall or light rainfall? So we're going to go up from 70 on the horizontal axis and see which curve we encounter first. Well, the first curve is for a 6 inch rainfall, kind of a heavy rainfall based on the comparisons here, and that yields about 42 bushels per acre. And if we go up next to the 3.5 inch rainfall, we get about 46 bushels per acre. And if we go up all the way to the top curve of 1 inch rainfall, we get about 62 bushels per acre. So it looks like the highest yields come from cool temperatures when the rainfall is light. Okay, now let's skip over to exercise 5. This will give you a chance to draw your own graph instead of reading a graph. And here we have a lab technician that's conducting a stress analysis on some copper wire samples. The sample length is recorded under various loads as recorded in the table. And we have to construct a graph. So the first thing we need to do is identify the axes, right? And the scales. So here we've done it. We've set up a load on the horizontal axis because that seems to be the independent variable. And the stretch in inches will be on the y-axis. And we've scaled this so that it'll accommodate all of our data. From 0 to 0.8 will in fact include all of the data that's in our chart. And from 0 to 16 pounds on the x-axis will in fact include all of our data. Now we're ready to start plotting our data. So here's 0 and 0, 2 and up to 0.02, 4 and up to 0.04, 6 and up to 0.04. We're not getting up very high, are we? 10 over to 0.1, and 12 over to 0.13, and then 14. Whoa! 14 went way up to 0.64. And we connected those with a line, and something looks pretty strange here, doesn't it? So looks like we've reached the load limit for this wire, and now we need to find the load at which we think the wire will probably stretch to the breaking point. Well, it looks to us like something really strange is happening right there between 12 and 14 pounds of load. So it looks like that would probably be the load limit for that wire. You wouldn't want to put anything stronger than 13 pounds on that wire. Alright, can we estimate the stretch at 3 pounds, even though we don't have a dot there? Well, we can certainly go up and hit that graph and scoot on over, and it looks like it's going to be pretty close to 0.03. How about for 16 pounds? Whoa! Now to do that, we're going to have to extrapolate, and because things are happening really strangely on this, just don't think it would be a very good idea to even guess. I mean, that curve could go straight up, or it could sort of flatten out. Who knows? So Extrapolating in this case is not a very wise idea. Alright, so that concludes our treatment of graphing and rectangular coordinates, and I know now that you've got enough confidence to finish the rest of those practice exercises and get really good at drawing graphs and reading graphs and interpreting those graphs. Good luck in that, and we'll see you next time.